In this video, we will talk about the power rule, the constant multiple rule, and the sum and difference rules. So these are going to be some derivative shortcuts that let us more quickly evaluate derivatives rather than having to use the limit definition each time we want to compute a derivative. So let's start with the power rule. This says that if n is any real number, then the derivative of x to the n, remember ddx means take the derivative of, and x is my variable. The derivative of x to the n power is n times x to the n minus 1. So the way I remember that is the power, the n, comes down in front, and then I subtract 1 from the exponent. So I have the n in front, and my new exponent is n minus 1. So I'm going to highlight this. This is a really important derivative formula. In the case where n is a positive integer, we can prove this with what's called the binomial theorem. The binomial theorem from pre-calculus. Due to time, I'm not going to do that in our lecture videos. I want to focus more on being able to apply this formula. In the case where n is any real number, so not just a positive integer, it's still true, we could prove that using a technique called logarithmic differentiation. Okay, this technique, we may briefly see it in, let me just say later in this chapter, chapter 3. All right, let's look at some examples. All right, so let's practice using this power rule. Part A, okay, I want to evaluate the following derivatives. Part A says, let's do the derivative of x to the 23rd. So ddx of x to the 23rd. Well, the power rule says, okay, I have x to a power, and the power is some real number. It's a constant. I can bring that power down. So I'll get 23. And then I have to do x to the, and subtract 1 from the power. So I'll get 22. And that's it. So before, I would have had to do that whole, limit definition of the derivative. And for something like x to the 23, that's going to be kind of challenging to do. So that's one of the reasons why the power rule is so useful. It makes doing derivatives a whole lot quicker than it used to be. But it's still important to know the limit definition of the derivative, because even though I haven't done these proofs, at least in the case where n is a positive integer, if you want to prove the power rule, it actually requires you using the limit definition of the derivative and just showing that when you do that, you will get nx to the n minus 1. So this power rule is predicated, it's based on the limit definition of the derivative. So it's important to know that still. All right, let's do part B. So B is saying, what's the derivative, ddx, of 1 over the 5th root of x? So right now, that doesn't look like x to a power. Let's rewrite it to put it in that form. I can rewrite this as 1 over, and the 5th root is x to the 1 over 5. And now let's bring the x term to the top, and that'll give me x to the negative 1 over 5. And I need it in this form. I have to have x to a power where that power is just some constant to be able to use the power rule. Because now I bring the power to the front, negative 1/5. I bring it down, and then I get x to this power minus 1. That'll give me negative 6/5. And that's my derivative. Let's do this last one, part C. What's the derivative, ddx, of pi to the 200? I want to give you a chance to try this one. Pause the video for 30 seconds to try this one. 4, 3, 2, 1, pause it, and try part C for 30 seconds. Alrighty, so hopefully you did that. Hopefully paused it for 30 seconds to try this. So if you said 200 pi to the 199, that is not right, unfortunately. But it's not a bad guess. So the reason why is the power rule, to be able to use it, we have to have our variable x being raised to the power. But in this case, it's not x to a power, it's pi to a power. And pi is just some number. It's 3.14 something. And pi to the 200 is still just some fixed number, which means this is a constant. So remember, when we take the derivative of a constant from the previous video, that is 0. So we can't forget our previous rules for derivatives. All right, so next we're ready to state some more rules. So for these, I need some preliminary information. If c is a constant and f and g are differentiable functions, so we know what it means for a function to be differentiable at a point. We talked about that in a previous section. When we say two functions are differentiable, just in general, this means they are differentiable everywhere. Differentiable everywhere for all values of x. Okay, so there are a bunch of rules in this section. Whoops. So we're ready to state a few more derivative rules. Okay, so the constant multiple rule is about if you have the derivative of a constant times a function, it says you can take that constant in front of the derivative and get c times d dx of the function. Okay, the sum rule says if you're taking the derivative of two functions added together, you can just do the derivative of the first function and add that to the derivative of the second function. The difference rule is really similar. It says if you do the derivative of two functions subtracted, that's going to be equal to the derivative of the first function minus the derivative of the second function. Okay, and there's also what's called the product rule, which is for the derivative of a function times another function. It would be really nice if this is just the derivative of the first function times the derivative of the second function. It turns out it's not that easy, or not that simple, but we'll see this actually in section 3.2. There's also a quotient rule for the derivative of a quotient. Quotient just means when you're dividing two things. So the derivative of f of x over g of x. This we'll also see in section 3.2. And we'll later see what's called the chain rule, which is for the derivative of a composition of functions, when you have a function inside of another function. So this is for something of the form f of g of x, and we'll talk about the chain rule in section 3.4. But for right now, let's do another example where we apply these. So the example has this function, f of t, and we want to find the derivative of it. Okay, so if I start to evaluate this derivative, the rules from above say things like if I need to do the derivative, in this case I'm doing the derivative and my variable's t, if I need to do the derivative d dt of something like t to the 9 minus 7t to the 5, let's just focus on the first two terms, that's just going to be equal to the derivative of the first thing, t to the 9, and then minus the derivative of the next thing, 7t to the 5, which means I can just sort of do the derivative of each one of these terms individually and then put it together. Let me also just point out that for something like this, where I have a constant like 7 multiplying the rest of my function, because of the constant multiple rule, I can pull that 7 to the front and get minus 7, and then just multiply that by the derivative of t to the 5th. Okay, so we're going to use those ideas together, because essentially what that means is, take the derivative of each of these terms piece by piece. So for the derivative of t to the 9, using the power rule, the 9 comes down, and then I get t to the, subtract 1 from the power, so I get t to the 8. For the next term, the 7 is multiplying the t to the 5, so the constant multiple rule says, well, just keep the 7 there, and multiply that by the derivative of t to the 5, which using the power rule would be 5 comes down, and then t to the 4 after I subtract 1 from the power. For 12 root t, I got to rewrite this as a power. This is 12 t to the 1/2. Okay, and there's a plus sign, so plus. Constant multiple rule says 12 is multiplying that t to a power, so keep the 12 there, and now multiply it by the derivative of t to the 1/2. So the power is going to come down, the 1/2 comes down, and then I get t to the, after I subtract 1 from the exponent, I get negative 1/2. Okay, the minus 3 is a constant, so that derivative is going to be 0. All right, doesn't really matter if I put minus 0 or plus 0, because it's just 0. And then for 4 over t, I have to rewrite this one as well as a power. This is going to be 4, and when I bring the t up, it'll be t to the -1 power. So doing the derivative there, the -1 will come down, and I'll get -4t, and then to the -2. I can simplify this a little bit to get f prime of t equals 9t to the 8 minus 35t to the 4. 12 times a half, that's 6. 6t to the -1/2. And then minus 4t to the -2. And it's fine if I leave negative exponents in there. So this would be my derivative. In terms of our goals, we finished goal 2, which is applying the power constant multiple and the sum and difference derivative rules.